My talk is going to be somewhat different than many of the earlier talks over the last, over yesterday and this morning. There's not going to be any particles or colloids in my talk, but it will have to do a lot with interfaces. I'm going to be talking about a resonant instability, and the people mentioned here are postdoc or graduate students, and they have, or a visitor, and they've been extremely instrumental in helping me get this talk together. Dipin Pillai, who is a postdoc and will be looking for a faculty position soon. Kevin Ward was a graduate student, graduated, now works for an interesting company called Gore-Tech, making smart clothing in the heat, mass, and fluid mechanics division. Nevin Brocious is a NASA fellow and a graduate student. Trey Batson was a former graduate student and works in a company in Colorado. And V. Devakar was a visitor, and he was a collaborator while he was in France, and he's currently now in the Jawaharlal Nehru Center for Advanced Scientific Research. So I'm grateful to all of them. Now, the talk that I'm going to present will be effectively in three parts. The last two parts will go fairly quick, are connected. So it'll have to do with resonance coming from mechanical forcing, resonance coming from electrostatic forcing, and then a combination of the mechanical and the electrostatic forcing coming in the way of levitated drops. One might wonder to get an example of a Faraday instability. And to do this, what I'm going to have you look at is to look at this this figure on the left, on the bottom left, under Sir Michael Faraday's portrait. Underneath, you'll be able to see two. I'm not sure how to operate this. Yeah, you'll see two liquids. Okay, and there's sort of a graph paper at the back, which I ask you to ignore. But there's two liquids, and you can barely see an interface. The whole container is going to be moving up and down. And as it moves up and down, you might see a slight deflection of the interface, but nothing really dramatic. The right container is going to move at precisely the same frequency as the left. In fact, it is the same container, but moving at an amplitude of motion of about 0.5 millimeter more. And you're going to now see the interface deflect fairly substantially. So what has happened is in the right container, we have attained a state of resonance. So to understand resonance, we might look at the schematic where we have effectively a gravitationally stable arrangement of an upper light fluid on top of a lower heavy fluid. And what we might ask ourselves is, how does resonance occur? To see how resonance occurs, let's not immediately imagine that we're going to vertically oscillate this system. Rather, look at the stably stratified system, static, and then give a perturbation to the interface. And when you give a perturbation to the interface, there's going to be, of course, these deflections with crests and troughs, and you'll get flow. You'll get high pressure under the crest, causing flow to go from the crest to the trough. And so the crest will become a trough, and the trough will become a crest. And if there was no viscosity, you would just get a permanent periodic motion of this going up and down. The frequency of that motion is the natural frequency for an inviscid layer. If you have viscosity, you will see a decay of that. And in the last gasp, as it's coming down to its end, that would be what we would consider the natural frequency, something that you can calculate from the eigenvalues of the perturbation of a fluid, okay, fluid layer. On top of that now, if you decide that you're going to impose this external oscillation, if the frequency of the imposed or the parametric frequency is commensurate with the natural frequency, the system will go into a state of resonance. So it's almost like having a pendulum. I should have brought a pendulum with me. We have one in our lab now, constructed with a 3D printer. It's kind of interesting. So if you have a pendulum with a base plate, and the base plate is also moving up and down, then you can get at an appropriate frequency for the pendulum to go out of whack, okay? And that would be the state of resonance. So it's very simple. It's a very simple matter, in a matter of a few minutes, to derive this expression for the natural frequency, and it goes as it is going to be negative. The frequency squared will be negative, since the fluid here is depicted to be inviscid in this formula. And rho 1 is the density of the bottom fluid, rho 2 is the upper fluid. So delta rho here is positive, and gamma is the surface tension. K is the wave number in an unbounded fluid of unbounded horizontal extent. You can see that the heights of the fluid, H1 and H2, H2 being the height of the upper fluid and H1 that of the bottom fluid, play very little role if the heights are say maybe 3 or 4 times that of the wavelength. So that's plenty. So this cotangent H term will go to 1. So sigma squared being negative, of course, implies that you see oscillations, permanent oscillations. And the important thing to notice here is that for ordinary fluids, typical fluids that you would run in an experiment, the gamma KQ term is subservient to the delta rho GK term. So it's very difficult to bring in the effect of surface tension unless you have very, very narrow containers. Extremely narrow containers. Okay, that's going to be an important thing to notice as we go along. So if I were to take these containers and typically shake them at different frequencies, you can actually get different modes, different patterns can arise. I will discuss how these arise in a few moments. And the sort of patterns are graphed on the right. I want to point out that these patterns can be predicted fairly accurately, and all that is different in these 4 diagrams is the different frequencies for the same system. But the other thing that I want to point out is that the fluid state that you have here saturates to a nice pattern. That's not always true. You can run a system such that the mode that you get does not quite saturate, and in fact it will break up sort of catastrophically. And so if we look at this for a few seconds, you are about to see the lower fluid, which is heavier, not just invade the upper fluid, but now actually break through the interface. So you're going to see what we will term later on as a subcritical instability. Going back to my figure, the equations that you use to model this are fairly standard. There's nothing, they're actually plain vanilla. There's nothing, absolutely nothing unusual about them. The important thing to notice is that you would ordinarily look at the system in a moving frame. And when you go to a moving frame, you, I'm kind of through this. Yeah, it's just this. There you go. Yeah. When you go to a moving frame, you adopt an extra term coming from acceleration, coming from the DDT term in the moving frame, and that is your acceleration, a omega squared, a being the amplitude of the motion of the container, omega being the frequency of that parametric frequency of the container. And so a omega squared is your acceleration that comes in because you're in the moving frame, and so rho a omega squared is going to be important. So where's it going to play a role? It's going to play a role ultimately when you look at the boundary conditions. And so let's go over the boundary conditions. They're also fairly simple. The first 4 are simply pointing out that you have no flow and no slip at the top and bottom walls, but the most important boundary condition is actually the norm. I'm playing games with this. I can see I'm not good at this at all. Is that the normal component of the force balance is where all the action is, and when you, it is very typical in these forms of studies, as we have seen in the last couple of talks, to first look at the linear stability and then do something nonlinear, but in the linear stability region, when you perturb the pressure, the base pressure comes in, and the base pressure will contain that term that we had earlier, i.e. the a omega squared term. So it'll come as a omega squared times delta rho, and that is going to be the very reason why you will start to see the instability. So the instability is going to come in with this delta rho, just like Rayleigh-Taylor does. Now, what is the signature, the results that you see? The important thing that one will notice is when you have resonance, the manifestation of the flow that you see if you have something unbounded is a subharmonic type of motion. So you excite something with a certain frequency, and what you see is first subharmonic. But you can get harmonic tongues as well. You can. So the type of result that you get is that of a critical amplitude, and from this linear stability result is a critical amplitude versus a wave number. Now, of course, when you have an unbounded system, it is the lowest point, i.e. the here, which corresponds to a subharmonic given by 1/2 omega that will trigger first. But in fact, when you have a bounded system, you can get all manners of harmonicity. And that's going to be the focus of the next few minutes of my talk. So what you have here is, let's say in an actual experiment, because experiments are not really unbounded, and you don't even want to make them for some reason. So let's say you're interested in looking at discretized modes. You would typically take an experiment of a certain radius, fluids of certain heights, and ask yourself, okay, in that radius of a container, I'm going to fix the frequency of the motion and ask myself what are the various modes that I can get. And you keep increasing the amplitude until the most unstable mode begins to manifest, okay? So that's fairly obvious. Now, what comes out of that is this rather incoherent looking graph. Okay, so this is a theoretical graph. This is not an experiment. This is all theory, and it comes entirely from the earlier one. So this curve is coming entirely from this, except here I have fixed the frequency and drawing the amplitude versus the wave number, and here I am fixing the geometry and drawing that same amplitude versus the frequency of the input. What we've marked here are two things. We've marked here the modes. And I'll tell you what these modes mean. You get modes, well, the first index on the mode is the azimuthal mode. This is a circular container. The second index on the mode is the radial mode, okay? Now, what happens is you have all these wells for every mode. So you have a down and you have an up. And there are places where you have codimension 2 points, i.e. effectively you've got places where more than where you can have two patterns competing at the same frequency. So you might want to know what happens experimentally. A typical mode. So let me show you what typical modes look like. I'm going to point out to you here. I've got somewhere down here a 0-1 mode. I'm not sure where it is. Yeah, here it is, a 0-1 mode. And I have a 2-1 mode to the left. So let me show you what that means. The 0-1 mode is fairly obvious. It's an axisymmetric mode. The 2-1 mode goes like this, just like my hands are going, okay? So that's the 2-1 mode. Now, you might ask, what am I going to see in an experiment, and how can I compare this experiment to this sort of a calculation? The experiment is also fairly simple. It's effectively only a shaker with a counterweight. And the key thing is you simply have a container with two liquids with an interface, and you have a camera looking at it. It really is a cheap experiment. Okay, so what you do is you run this at different frequencies and you plot. And here's the plot. So what I have here is, again, the theoretical, whoops, there I go again, is again the theoretical plot with the solid line, and these circles represent the experiments. So you can see that the experiments actually are very, very close to the theory. Now, there's a long story to that, and I can talk about it, but there's a region where it is not, and that is not an accident. Okay, it is not experimental error or anything like this. The error bars, by the way, are actually too small even to be depicted. This was done extremely accurately. The way the amplitude was fixed in this experiment was by using an old-time favorite, what we call all threads. You have a threaded rod with a lot of threads per inch, and so you can very, very accurately determine what the amplitude is going to be. And so there's really not much error at all. This is a result of maybe tens of experiments. But I'll be happy to talk about this in case anybody anybody has a question, but the main message to be taken from here is that you do have extremely good connection between the theory and the experiments. The second message is this. Every mode has a down and an up, and the negative slope is one that will be connected with the overturning instability. In other words, the liquids will begin to exchange positions. The upper slope is the one where the liquids, where the same pattern will begin to saturate. So in other words, we have a range of frequencies for a given mode where one part of the range is going to give you catastrophic exchange of liquids, and the other part of the range is going to give you a saturated pattern. Here's an example of a saturated pattern. Okay, let's see if I can get that to go. Okay, this might take a few seconds, but I think it is running. Yep, it is running. And this is going to show a breakup, okay? And there you go. It's going to completely break up. Let me show you a case where now that earlier mode that I showed you earlier, right here, I'm going to show you a place where both these modes are now going to compete. So let's go here. Let's go. Okay, you're going to see both modes, and they're going to compete. And this is precisely at that point, that so-called codimension 2 point. So this was run at a point which I'll give you in the figure, and you can see it went to break up ultimately. It was running right here, right where that last dot is. Let me see if I can get this here, right here. It was precisely at that point, okay? And that's where you had it. So you could pinpoint exactly where you want to see these codimension 2 points. And they have value in mixing. This is extremely important in microfluidic mixing. This is why this whole problem was of importance to us. So ultimately, what I can say thus far is you have very good agreement between theory and the experiment. That there's no doubt about that. But we do see something which is interesting, that you have this fluid exchange along the negative slopes. It is something that we're trying to understand. It's not a question of not knowing how to do the theory. You can do a weak nonlinear theory of Ginzburg-Landau, but you'll get a whole variety of terms. It's not very clear that it's going to be revealing. So we are looking at other possibilities to do that. Now, the other important thing is that the interfacial tension is not important. You see this theoretical curve which I showed. You have to input the fluid properties, of course, to get it. If you had changed the interfacial tension by an order of magnitude 10 times, the curve would not have shifted. This problem is entirely dependent on the delta rho. So if you want to bring interfacial tension into account, there are two things that you can do. One is the very obvious one. You can lower gravity, and you can do that in a parabolic flight experiment. So, but before you do that, you might serve yourself by doing a quick calculation. And what you will see is that these modes will shift to the left. So what you get from this curve is that the modes here, these are the modes that you would have gotten under 1G. These are the modes that you get under 0G. They all shift to the left. In other words, it's easier to see choppier modes in microgravity. And that's what we were able to see. This work was done by Divakar. You can see that on ground, the experiment would give you a lazy mode, whereas on space, you can see immediately choppy modes. Now, there's utility to this. We are very interested in using these choppy modes to enhance heat transfer in space-enabling operations. When you go to space, you don't have buoyancy. And heat exchangers, particularly heat pipes, will cause a burnout. So the idea is, can you send acoustic waves? Nobody's going to shake the intention is not to shake a pipe, okay? The intention is to go and send a signal. So if you can send some sort of acoustic waves, you can start to generate flow. So this is the result. You can actually see the interface beginning to turn. That was towards the end of the parabola, okay? So there are some questions. We don't know necessarily what the mode structure is. We only know that the modes have become very choppy. So the actual nature of the instability is not clear. Okay, so this is something which is of interest. So we ask ourselves, is there a cheaper way to go and find, to counter gravity and perhaps enhance surface tension? How am I doing in time?
20 minutes?
Oh, that's more than enough. Okay, so one way is to ask yourself, is there a better way for us to counter gravity without doing this expensive things of flying aircraft and risking your life and things like this? So, so you put two fluids between two electrodes. And I'm going to ask myself here, now I'm going to impose, I'm not going to shake the system. I'm instead going to impose a voltage drop across it. Now, I can impose a constant voltage, put a DC, or I can put an alternative field, or I can put a combination of the two. If I put just a DC field, what will happen is the voltage drop creates a Maxwell stress. The Maxwell stress goes as the quadratic of the voltage difference, and it will cause a form of pillaring, okay? Pillaring that has been observed by some people, whom I will mention momentarily. On the other hand, if I put an alternative field, it also goes as a squared cosine squared omega t. So that's important. This a squared cosine squared omega t, using the double angle formula, becomes a 1/2 a squared plus a 1/2 a squared cosine 2 omega t. Consequently, my response, which used to be which I used to say subharmonic, would be half of twice harmonic. Okay? So in other words, it'll be harmonic. So the lowest will be that. So on the other hand, if I have a DC and an AC field, I will truly have a subharmonic. Now, what is the natural frequency? The natural frequency when you have electrostatics is very close to that of when you have electrostatics, with a key difference. So I'm going to take the same natural frequency, and you can get an analytical expression if you ignore viscosity. Okay? Of course, our calculations with those curves that we had did have viscosity into account. The first part is something you already saw. That's the mechanical frequency. The second part is new. This is the electrostatic term, where epsilon 2 represents the permittivity of the upper medium. If it's air, it's the permittivity of air. Epsilon naught is the permittivity of free space, and D is the voltage. If it were a direct, if it were non-oscillatory. If you had an oscillatory voltage only, D squared would be replaced by 1/2 of A squared. Okay? So this term is opposite in sign to the first term, and that's key. In other words, my electrostatic term can actually counter gravity, counter it enough that it can make surface tension more important. And that's going to play an important role for a very useful application. What does this look like when you run an experiment? A typical experiment will look like this. It's actually a very inexpensive experiment. All you need to do is to have a container with a bottom electrode, okay, a dish containing a fluid, and a top electrode. That's it. You can charge it, and ideally you would want this upper electrode has to go touch this, of course. And this is what you see. You can get these sorts of modes just like you got in the mechanical, and you can predict them too. Okay, so the theory for this is, of course, slightly different than what you had in the mechanical. There is no question of going to a moving frame, but what you do have is the Maxwell stress, which I've pointed out here. And you've got a term for del squared psi. So this is the case of the leaky electric, the leaky dielectric, which simply means that no charge is being contained inside these fluids. The charge that is being imposed by the plates is finding its way only to the interface. It is an approximation. Okay. Now, these sorts of equations can be modified with charge, with ionic fluids, if you wish. The best reference for this is by Dudley Seville. There's also Melcher and Taylor. Okay, and ultimately, all these equations are ones that we normally use, and we've seen before. These are the mechanical equations of normal stress, and what you have at the bottom is a charge generation equation, and of course, charge conservation at the interface. It is in this normal component that the Maxwell stress will come in and play a role. It's there. Okay, so our response here is going to be almost identical to what we had before, but we're now going to plot the amplitude of the AC voltage, which is now in kilovolts, versus wave number. And this is now for a water-air system, typically of a few millimeters of height of water, and air being passive, being a good dielectric. Now, what you see are, unlike the mechanical Faraday, an early an early sort of tongue, not quite like these tongues, which are subharmonic and harmonic and so forth. Okay? This tongue is called a pillaring tongue. This is what you would have seen when you had pure DC. And this line here, the dotted line here, is what you would see if you had pure DC. This line here is shifted to the left in the presence of the AC. So what I have here is a DC plus an AC cosine omega t in this calculation. These pillars were seen by Gambhir and Thaukar, and also by Roberts and Satish Kumar. What we did was we took this and we have included inertia. So the earlier works did not have inertia, and you need inertia in order to see resonance. Without inertia, you will not see any resonance at all. So we had this, we've now taken this resonance in the long wave theory, and I'm going to talk about these 3 points, the triangle, the circle, and the square, and to show you depictions of what they look like, and then show you an experiment. So the first is that of the pillar. In the presence of the AC, this pillar is not just going to form a single pillar, it's actually going to keep going like this. And if the holdup of the liquid were large, this pillar would go and touch the top electrode. Okay? Now, what you see next is simply going to be subharmonic Faraday waves on the left and harmonic on the right. And in fact, when you do imaging, you actually look at it using a camera and use image J, and that's how you determine. So there's nothing really quite unusual about it. Now, let us say that you went now and had a thin film, okay, on which you impose this just pure DC, just out of curiosity. Now the film is thin, you have pure DC, but you also have some inertia now deliberately in this system. What's going to happen is if you run this, you will get these pillars. And this is akin to Rayleigh-Taylor because you put in so much of electrostatic effect. It's countered the gravity. It acts like Rayleigh-Taylor, except it's not hanging from above. This is just a liquid film, and see what you get. You get sliding. This sliding has been seen by Lister when in the pure Rayleigh-Taylor problem, and conjectured by him to have been a result of a symmetry breaking bifurcation. It was shown only recently by Dietze-Picardo in a study in JFM that this was actually due to asymmetric perturbations on a symmetric shape. Okay, and these calculations were done by Pillay recently. Okay, so let's go to the experiments and see what the experiments will tell us about these sorts of about what we just saw here. So it's again very simple experiment. Really, all you have is 2 liquids, and with the conductor hot and bottom plate, and they're just connected directly to a high voltage amplifier. Seen here, this was a setup we had in JAXA. Okay, and here's the container. You put the container right on top of this, and you increase the voltage. That's all you do. You have here, how am I doing in time, Herbert?
12 minutes and 19 seconds.
It'll be done sooner than that. Okay, so you now have, you can see the different modes, the Faraday modes of subharmonic and harmonic. Okay, and this is typically what you image. And all you're looking for is the onset point for this image. And it's amazing how much linear theory can actually tell you. Okay, usually, I mean, we can be skeptical very often, but it really tells you a lot. Now, if you take these fluids, now make them deliberately very large in extent, horizontal extent, you can plot the amplitude versus the frequency in a theoretical curve, and you get this line. This is the theoretical line. And these little dots here are the experiments done for a system of silicon, oil, and water. Now, what is it that we learn from this? Something amazing, which is the following. To see whether surface tension really is playing an important role, you can do the same, not experiment, but calculations by increasing or decreasing the surface tension. And you will see that the best curve that you have is for the nominal surface tension that you would have measured. So if I went to a pendant drop tensiometer, measured the surface tension, I would be able to generate a curve which would be pretty close to the experimental results. How can I use this? I would not be interested in using this electrostatic way of resonating to measure surface tension, interfacial tension between silicon, oil, and water. But this turns out to be extremely important for systems where it is almost impossible to measure interfacial tension. And that is when you're having say, semiconductor like gallium arsenide encapsulated by boron oxide. Those of you who might be aware of crystal growth, there are a couple of ways to grow crystals. One is called the Bridgman method. The other is called the Czochralski method. And when you have something like gallium arsenide, the arsenic has a very high volatility. So to contain the arsenic, you put boron oxide. So you immediately have an interface. And that interfacial tension there is extremely important. As the fluid gets thinner, it gets thinner as it gets chewed up and being made into solid. So that interfacial tension, people don't know how to, they guess it, okay? And they make some rough calculation. This is the best way to actually measure the interfacial tension. So this is really something that we have been quite excited about, that you actually have a new way and a fairly accurate way. So the result so far is that you can actually find a very good way to measure interfacial tension that will have good application to gallium arsenide and boron oxide and things like that. There's not only those two substances. There's also other things like indium gasum, like gallium phosphide and so forth. So the idea is that these are very high temperature. These are you can only have gallium selenide in its liquid form at about, I think, 1100 or 1200 degrees Celsius. So you can't really put these in any ordinary tensiometer. However, subcritical motion is something that we never saw. And we believe that we now, in this case, know why. And I'll be happy to talk about it. Now, there's one more last way to measure surface tension, again using resonance. This time where I'm going to use an electrostatic field to levitate. So let me tell you what the experiment is about. What I have here is a comic on the left. Okay? I'm going to take 2 electrodes, and at the bottom I'm going to put a small amount of metal, let's say zirconium. I'll pull up the metal using a DC field and levitate the metal in a furnace. Okay? The furnace is not yet turned on. Then you heat the metal with a YAG laser, and the metal will, of course, melt completely and form a liquid drop. Then what you do is you deliberately change the field ever so slightly, alternate it, so that this metal moves up and down about its centroid position ever so slightly. And when it does that, okay, moving up and down like this, and you can keep increasing the frequency. At a certain frequency, the drop will begin to undulate into prolate oblate form. And on the right are the groups of the 3 students, Nevin, Kevin, and Evan. So in case you wondered, okay. Yeah, running this in a NASA furnace, because we couldn't afford a furnace like this. And what I'm going to about show you now is an actual experiment. So what I have here is an actual experiment. And this is an image taken from the furnace at 185 degrees Celsius. Slight variation, it's just moving up and down, nothing much that you could tell. At 185 hertz, okay, you're now going to see, this is now at the resonant frequency. It really is changing substantially. And now you go to 191 hertz, which is the next one, and it's very slight again. So there's only really one frequency where you got this substantial change. So if you were to plot it, you would actually get something like this. On the left, you would actually start to say, if you were to plot it, you would see a sudden sharp change, because what you're plotting here is the normalized maximum diameter, which when it's a perfect sphere is equal to 1, which is out here. And so you now see that there's a certain frequency, say 185 hertz, where you get this sudden change. Now, you could go to a very inexpensive formula created by who else? And in fact, this is again the natural frequency of an inviscid sphere. And you can say, well, is this drop inviscid? Well, surely not. It's a liquid metal. But its density is so high that its kinematic viscosity is extremely low that you could pretend that it was almost inviscid. This equation does suffer some change. You can include charge effects, which in this case will not amount to much because it's a good conductor in contact with a vacuum. You could run these experiments with something else, with water also, and you'll get all sorts of modes. So you can do this. And in the last slide, I wanted to show that last but one slide, I wanted to show that we have actually checked this for various metals. And the literature has also produced some numbers, which we believe are actually wrong, even though they're a little bit higher than us. And I'll be happy to discuss how they have found, how they actually measure the surface tension for these things, and it'll be quite surprising. The overall conclusion of what I wanted to say was this, that this is really the first time that we've been able to achieve a very good agreement between the electrostatically forced Faraday and experiment. And that you can actually use both of these in micro mixing and in space applications, such as in enhanced heat transfer. But the key, really perhaps the best application, is that you can use this for interfacial tension, something which is very important for additive manufacturing. It's getting more and more important now to use additive manufacturing with metals. And you create these pools, and you want to make sure that they don't create ripples and things like that, that you're operating at the right Weber number limit. Well, you won't know what the Weber number is if you don't have the surface tension right. So that's really what it is. And what we don't know, and the real question that we are asking now, is when do we get catastrophic behavior in resonance, and why actually do we get it? I do thank these agencies. There was an interesting funding agency, the Chateaubriand, which normally is known for its wine, actually has been interested in funding students. So we're pretty grateful for those of you who drink a lot of wine. Thank you. Watch out, this is it's a dangerous step here.
Yeah, it's a bad step. Questions?
Okay.
You gave a very nice description of the equations and boundary conditions, but you didn't say much about how you treated these. What kind of solution method?
Okay. For the linearized theory, it was fairly straightforward. We just linearized the equations about the base state in the moving frame, which is first it was all linear stability. But what you saw later were long wave approximations to track the evolution of the interface. That's when you could see the pillaring and things like that. Those were done based on what was called the WRIBL, the weighted residual integrated boundary layer technique, a technique that was, I guess, promoted by Manville first. Okay, so that's what we use.